So I started recording, and now we can continue with the second hour. We have seen linear time invariant systems and their responses to inputs. How did we do that? Let us remember what we did in discrete time, and we will try to extend it into continuous time, because that extension is technically the best way to understand the formulas and other algorithms in continuous time. If we start continuous time, it's difficult to understand that way. So first we wrote our input signal x of n as a linear combination of scales or scaled and shifted impulses, right? The shifted impulses, these delta n minus k's are impulses at k. And what's the value at impulse at k? It's xk, the value of the signal. So we write our signal in terms of impulses like this. And we call this a convolution sum. It's not a convolution, it's a convolution sum. Or you can think of it like convolution with an impulse, which gives you the same signal. And when you feed this into a linear and time invariant discrete time system, the output will be the same linear combination from minus infinity to plus infinity with the same scales of individual impulse responses, shifted individual impulse responses, h of n minus k. Okay, so this is what we found. And we said that this is the convolution of x of n and h of n. That's how we developed the formula for convolution in discrete time. Now, can we do the same thing for a continuous time signal is the question. And you have to follow very carefully what I'm doing here. I'm going to write x of t again as a linear combination of continuous time impulses scaled by the value, the coefficient of the impulse will be the value of the signal at the impulse position. First, let me write the impulse. Let's say delta t minus tau. This tau is like the summation variable. It's just like saying delta n minus k. Instead of k for discrete time, I'm using tau for continuous time. So delta t is shifted by tau. So it's an impulse at tau. This is an impulse at tau. And what is the scale corresponding to that? It is the value of x of t at t is equal to tau, which is x of tau. So x of tau times delta t minus tau. It's like saying xk delta n minus k. And I have to combine them, but it's this time a continuous combination. So I'm integrating. Okay. This formula is, as you see, quite relatable to the discrete time. Instead of a discrete summation, now we have a continuous integration, but it's the same linear combination, essentially, what we get. Instead of these delta t minus tau, you may think of it like a Riemann integral, where it's an arbitrarily small rectangular box shape. And by stacking the rectangular box shapes, I'm almost obtaining a continuous time, continuously varying signal. But those rectangular boxes are just very narrow. They make impulses. Now, if I feed this into this time a linear and time invariant continuous time system. So the system impulse response was h of n in discrete time. Here, the impulse response is h of t. So delta t comes into the system and ht goes out. Okay, that is the impulse response. Same logic. Impulse is the input, response is the impulse response. Therefore, for delta t minus tau, what will be the output? If the input is delta t, the output is h of t. If the input is delta t minus tau, what is the output? it is h of t minus tau. So for this, I will get h of t minus tau. Okay. Now for x tau, a scale, times delta t minus tau, what will be the output? The output will also be scaled with the same scale, which is x of tau times h of t minus tau. So x of tau, delta t minus tau goes into the system, and x of tau, h of t minus tau goes out of the system. How about if I combine all those separate x of tau, h of t minus taus for different taus, ranging from minus infinity to infinity? When I combine them in the input, I have to combine the individual outputs at the outputs. And this I will call y of tau. No, not y of tau, it's y of t, excuse me. Now, because of d tau in the integral, tau will go away. It's just the running integral of the running variable of the integration. And the only thing that it is parametric to will be time, y of t. Okay, so this is, let's give the name to this one. And remember the names of these ones too. This one was convolution sum. And this one was convolution of x and h. And the below integration terminology is convolution integral. And this formula itself is, again, convolution. Just like in discrete time, but this is continuous time convolution, of course. And the notation will be the same. Y of t is equal to x of t convolution with h of t. But now it's not in the form of a summation, it's in the form of an integration. All right, this is what is happening in continuous time. And we can start with an example of making a convolution, implementing a convolution in continuous time. And that example will already be infinite extent. So finite extent convolution will be easier than this example, but this is at least something analytical, algebraic expression, which will be also helpful for understanding the convolution, because I will apply this x of t that I will give you and this h of t that I will give you and put it into the convolution formula, which is that integral that I just wrote. And here x of t is equal to e to the minus at u of t. Imagine what it looks like. Just visualize it in your eyes or in your brain, and I will also try to draw it. And this is the input, and we have a linear and time invariant system which has an impulse response. H of t is equal to u of t. So the impulse response is interesting. The impulse makes a perturbation to the system, and the system just jumps to the value 1 and then stays there. It doesn't go back. Maybe there's a capacitor that fills up and it never discharges through any resistor or anything else, something like that. So these two, and the question is, what is the convolution of the two? And I will do it without drawing or anything. I'll just put them into the formula, which is telling me that y of t, which is the convolution of x of t and h of t, is equal to, from minus infinity to infinity, x of tau. Let me write it. Nothing, just blind way of doing things. E to the minus a tau u of tau. Okay, and then h of t minus tau, which is u of t minus tau, because h of t is u of t. and d tau. Now, what is this? There are a few things that we must notice. It's very critical to analyze these things, U functions, because they will be reflected to the upper and the lower bounds, okay, of the integration. U of t is showing me the starting point, where to start and where to end in this integral. Otherwise, it's from minus infinity to infinity. But for some values of tau alongside this integration, the inside integral argument becomes 0. For example, from this U of t, I can say that tau must be greater than or equal to 0, right? Because if tau is less than 0, U of tau will give me 0. And it's in the multiplication form inside the integral. Therefore, the integral is enforced to be tau greater than 0. So this starting point must start from 0, or it must end at 0, whatever. No, it must start from 0 and onwards. So the lower bound of the integration is 0. Now, how about this one? U of t minus tau. First of all, there is a minus tau. We have a U of minus tau, and U of minus tau is a left-hand-sided unit step, like this. And it starts, or leftwise starts, from t along the tau axis. This is U of t minus tau, okay? It's all ones from minus infinity up to t, for all tau values from minus infinity up to t. But if tau is greater than t, notice that t minus tau becomes negative, less than 0, which means it becomes, U function becomes 0. So it is 1 for, this is 1 for tau less than t. So tau must be greater than 0, and it must be less than t, right? That's interesting. So I change the integration from 0 to t, because it must be greater than 0 and less than t. And inside that one, I have e to the minus a times tau. And within this range, U of tau is 1, and U of t minus tau is also 1. So I don't need to write them. It's just a multiplication with 1, and I have d tau. Okay, this is the integral that I have, e to the minus a tau d tau. And it's an exponential term, and its integral is something that we know from calculus. It is minus, because of the e to the minus, the minus 1 over a times e to the minus a tau. Let me write it. It's minus 1 over a e to the minus a tau, tau ranging from 0 to t. So this is the definite integral. It's not an indefinite integral, which will give me some numerical results. By the way, notice that the t for this one must be greater than 0. Otherwise, the integral from 0 to t will be invalid. So if t is less than 0 in this convolution expression, we don't have an integration range. Within that range, it means U of tau and U of t minus tau do not overlap. They are separated, and their multiplication is therefore 0, which means the convolution for t less than 0 is 0. But for t greater than 0, it is this integral that I'm writing. So at t, it is minus 1 over a e to the minus a t, okay? And minus, at 0, it is minus 1 over a e to the 0, which will give me because of this two negatives after the subtraction, this one makes 1 over a, and the other one makes minus 1 over a e to the minus at. I can put them in a parentheses of 1 over a in parentheses 1 minus e to the minus at. So this is y of t. But this is only for t greater than or equal to 0. So you remember the trick that I told you regarding how to write things in terms of signals and systems, or signal processing wise correct. It is this. The answer, I have to say, is y of t is equal to 1 over a, 1 minus e to the minus at times u of t. Now, it's a trick. It's a magical trick. I just multiply with u of t, and I solve the problem of defining this thing only for positive t, and for negative t, it is 0. It becomes immediately 0. So this is the answer. Notice that I solved the question without any graphical interpretation or anything. I just put the formulas into the equation, and from that equation, I solved the equation. It's an integral equation. I solved the integral literally, and I obtained this answer. Is there any question up to this part? Because this is critical. You should be at least able to apply the convolution sum or the convolution integral. And for that, calculus is necessary. You have to know integrals. If you don't know the integral of e to the minus at, or if you cannot solve definite integrals, it means you are in trouble. So I hope you know calculus. Do you have any questions about that?
Hocam bir soru sorabilir miyim?
Yes.
Hocam x'te eğer negatifte de tanımlı bir kısmı olsaydı x'te'nin, o zaman o küçük t'yi biz pozitif seçmek zorunda mıydık, yoksa negatifte alıp o iki integrali ayrı şekilde değerlendirip öyle mi çözmemiz lazım?
Well, as long as the two functions overlap, you have to define the integration limits accordingly. Of course, it doesn't have to be always positive like this. It became positive. I mean, the output is defined for positive t, or the integral limits only included positive parts, because both the input x of t and the impulse response h of t are right-hand sided, completely for positive, defined for positive t. But as you say, if h of t would start a little bit from the left, or if it is completely left-hand sided thing, then the convolution all the time. Okay, it may be negative, of course, because it's essentially from minus infinity to plus infinity. That's the correct integral. So the first integral with the green and the red arrows that you see on the screen, that integral is the definition. I'm just trying to solve it to come up with the result of this integration. And because of that, I don't want to use u. U of t is either 0 or 1. The 0 parts, I want to get rid of the integration over there. I don't want to define the integral to include those portions. And if it is 1, I don't put it. It is 1. So I simplified that expression into integration from 0 to t e to the minus a tau d tau. That's what I did. And maybe that's a good exercise. Solve this for h of t is equal to u of t plus 2. H of t is equal to u of t plus 2. It's a linear and time invariant system. Let's analyze some properties of this system. For example, is it a causal system? Somehow we came up with some old discussions. Causality. Is it a causal system? H of t is equal to u of t plus 2. Can you draw it? What does it look like? It's again a unit step function, but it starts from
Eksi
minus.
2'den başlayacak.
Yeah, it starts from -2. It makes a jump. But the impulse comes at 0. Although the impulse, the input comes at 0, its response appeared before that. 2 seconds before the input came, the response already came, already appeared. So this is not a causal system. The output didn't come after the input. It came before the input. So this is a non-causal system. H of t is equal to U of t plus 2, non-causal. But it's a system. I just give it in the exam like this, and I want you to solve for the expression for y of t and try to simplify it as much as possible. It's a possibility. Now, do it. Clearly, the integration limits will be slightly different, and you will not come up with such a compact and small expression. Maybe it will be a little bit larger expression, but it's manageable. So I would really do this. I would really solve this exercise that I give you. Now, I want to close this page if you have no further questions. Do you have any other questions from this? If not, then I will open a new page, because now we will finally for today discuss about graphical way of doing the convolution. And I will do it over an example. Okay, let's do it immediately on an example. X of t is given as, let me put it like this, 2 times u of t minus u of t minus capital T. In the previous years, I was using different ways of putting this, but for this year, let's just write it like this. The thing is, will you be able to understand how it looks like? U of t is a unit step starting from 0, and u of t minus capital T is a unit step starting at capital T. I'm assuming that capital T is positive, okay? So I subtract the second u of t minus capital T, which starts later, from the previous one, and what is remaining is the interval in between. So this is actually equal to 2 for the range from 0 to capital T, and it's equal to 0 elsewhere. It's a rectangular box, or you can visualize it as this. This is capital T, and this is 0, and this is x of t over the time axis. Now, if you are unable to come up with this x of t graph from the expression that I gave at the top, this one, then it means although you may know how to do further convolution, you won't be able to solve the question because you didn't understand the input signal. Okay, first try to learn the language of signals and systems, which are usually using u of t's for limiting starting points of a signal and for also limiting the ending points of a signal. This, for example, makes a box. And within this box range, I can multiply this with a sinusoid or a complex exponential, which will make a complex exponential that starts at one point, or an exponential which starts at one point and ends at another point, just cropped, chopped signal value. It's a trick. Use always the unit step functions. So this is x of t. And again, I'm gonna use this trick. I will say t times u of t minus u of t minus 2t. Now, what is this? First, maybe you have to analyze what's happening in the u part, the unit step parts. It's u of t minus u of t minus 2t. So it's a box starting from 0, ending at 2 capital T, right? Twice the length of x of t, twice the width of that. And then I'm multiplying it with t. What does that make as a shape? It makes this. H of t starts from 0, t at 0 is 0, and then from here to up to 2t, it's h of t is equal to t, which is a 45 degrees inclination, straight line like this. And it is cropped over there, and the rest is just zeros. So from 0 to 2t, it's just a 45 degrees increase because the function is h of t is equal to t. Therefore, at this 2t, the value reaches up to 2t, 2 capital T, okay? These two are the signals, and I want you to convolve these two. Now, how can we convolve them? We can, if you try to put these into the integral convolution equation, that's meaningless because during the convolution, the starting and ending points of the actually, so it's only by 0 and the time index t, the integrals from 0 to t, or something like that. But if the situation is like this, two finite bounded things, it is best to apply the trick that I have used for discrete time. Flip around one of the signals and slide over the other one. H of t minus tau. This h of t minus tau means we are flipping around h of t or h of tau and make it h of minus tau and then shift it by an amount of t. That's how we get h of t minus tau. So it's the same kind of approach that we will use. Let's come back to here. And I will flip around h of t. Although it is the longer one, let me just show it for as an example. You could also flip around x of t. We know that x convolution h is the same as h convolution x, so it doesn't matter which one you flip around. If I would do this in an examination, actually I would flip around the shorter one, which is x of t. It's not only shorter, but it's simpler. It's a straight box, so flipping around that one would be easier. But now I will flip around the triangular or the ramp shape of h of t. And I will draw it on top of the other one. I will draw these things again. So we have this 2 value going all the way up to capital T. And this is x of, well, actually, let's write it rigorously. This is x of tau. And then I will draw h of t minus tau. And then I will multiply them. Now let's start by taking t is equal to 0. So it will be h of minus tau. That is over the tau axis. Oh, it's not a t axis. I think this is wrong. It's the tau axis. So over the tau axis, I'm folding the h signal, h of minus tau. Let me draw it from 0 to this time minus 2t. And it's going to be like this. Okay. The flipped around version. Now, then I have to multiply x of tau, the top shape, and h of t minus tau. This is multiplication of the two signals, and then I will integrate the multiplication. Okay, this is what I will obtain. And I'm going to call it y of t. Now, for such straight line expressions, it is best to start with finding the starting and ending points and determining the value of y of t at those starting and ending points. First things first, when t is equal to 0, this is the starting point of y of t, because if I make t less than 0, it means I am further pushing this triangular shape to the left-hand side, and x of tau and h of t minus tau do not overlap. Nothing, okay? And since they don't overlap, it means y of t is 0. But starting from here, a question from Melcan. Hocam t kadar sola kaydırmamız gerekmiyor muydu? Yes. No. We shift by t. If t is positive, we shift to the right. If t is negative, we shift to the left, because it is h of minus tau that we are drawing. So h of t minus tau for a positive t would mean it is shifted to the right by t, and for negative t, it means to the left. So when t is less than 0, this will be shifted to the left, and there will be no overlap of this multiplication x of tau and h of t minus tau. Now let's make t is equal to 0 right here. Let's keep it here. The overlap is very marginal. It's nothing, in fact. So this multiplication is still 0. So y of t at t is equal to 0 is 0. I can write it like this. Y of 0 is equal to 0. That's something that I find. And everything before 0 is also 0. But after 0, when I shift a little bit to the right-hand side, let me see if I can use this. I will just move it. Something came into the selection, some others just didn't. And why is that? I'll try again. Hopefully, yes. Now I'm moving this, as you see, by some amount to the right-hand side. By what amount? That amount is t. Okay, it's here. Sorry, this is t. So for a t value, something between when t is less than capital T but greater than 0, it fits into here. So t is somewhere in this point. Now, what is the amount of overlap? The overlap is from 0, let's draw it with red, from 0 up to capital T, of course, but it ends at t. So from 0 to t, there is an overlap. Anything greater than t or anything less than 0 is zeros. And in between, I come up with some multiplication. I have to multiply these two. And the multiplication is this area, because one of the shapes was constant. This area scaled by that constant. What was that constant? It was 2. Okay. So twice this triangle area is the area under the multiplication part. We can draw the multiplication if you wish, like this. Not here, but here. T. And this is the area underneath. And this is the multiplication. This is x of tau, h of t minus tau. over the tau axis. This is the multiplication. The red figure is the multiplication. Do we all agree with that? Because now we have to find the integral of this. So we have to integrate this multiplication. Integration means finding the area of this multiplication. So what is the red dashed area? Let's look at the original h of t minus tau. It was a 45 degrees inclination, so I can see that this point is also t of the triangle. It's an equal sides triangle, okay, with 45 degrees inclination. And when I multiply it with the value, which is 2, like here, then this point becomes 2t. Is that okay? Now, the area then, the area is equal to 2t times t over 2. That's the area of the triangle, which is t squared. So I'm going to write it in green here. Y of t is equal to, it's equal to 0 for t less than or equal to 0. And it's equal to t squared when it's between 0 and capital T. Because it's the multiplication becomes like the triangle, and the area under the triangle is t squared. Now, let us try to remove some of the red things here. This one, this, and all of this. We can keep the rest because we are going to use it again. Now, I will use the lasso tool again, and I want to select this one, but I will move it further to the right, like this. Of course, I have to erase this, okay? Now, and I have to erase this t, because t is not here anymore. Where is t? T is here. I shift to the right by an amount of t. Where is this t? This t is greater than capital T, first of all, clearly, because capital T is here. But it is less than 2 capital T, because if that T is more than 2 capital T, it means something else. It means we have shifted too much to the right-hand side. So, like this. Let's keep it like this. T is greater than or equal to capital T, and it is less than 2 capital T. So it's this situation. Now, what is the multiplication? The multiplication is again cropped from 0 because of x of tau at the top. To the left of this line that I have drawn, this red line, it is zeros. And to the right of capital T, also because of x of tau, it is 0. So this is the overlapping portion. From 0 to capital T is the overlapping portion. If that is the overlapping portion, what kind of a multiplication crop do I have? I have this crop. Okay, from 0 to capital T. Okay, it's a parallelogram shape. Can you find the area under it? Because we have to integrate this multiplication. But we have to integrate twice this multiplication because the value of x of tau is, again, 2. So we don't only cut, but we also, after cutting, multiply everything by 2 because x of tau is 2. If x of tau, by the way, is a different shape, a different line, that you're in trouble. It means you have to multiply this line equation of h of t minus tau and the other line equation of x of tau and come up with a further equation for the multiplication. I'm literally multiplying the top shape and the slided bottom shape. Because sometimes students just assume that multiplication of the two just corresponds to cutting one of them. It's of course cutting, but it's also multiplying the values too. So this time the multiplication value is 2. We are getting twice of it. So what is the area of this red dashed thing? I will find twice that area. That area, this area is, first of all, we have a small green triangle here, okay, here, and a larger blue triangle here, like this. So the red area is blue minus green areas. That's how I will do it. Now I want to remove these things because, you know, I will shift it further. Sorry about that. So what is the larger triangle area? This point here is T minus capital T. And this point here is T, heights of that. So the small green area that I will subtract is 1/2 T minus capital T squared. This is the area of the small green triangle. And I will subtract it from T squared, which is the blue triangle, the larger blue triangle. 1/2, of course. And then I will multiply everything by 2 because of this 2 here. Everything is scaled, which will give me area is equal to, the 1/2's will cancel with the multiplication by 2. It will be T squared minus 2T plus 2 capital T plus capital T squared. And that will give me, T squares will cancel. It will give me 2 capital T minus capital T squared. And 2 capital T times T. Sorry, there is a times T here. I forgot, I'm sorry, while taking the square term. 2 capital T minus capital T squared. That's the area. So let me write it. 2 capital T minus T squared for capital T in between capital T and 2T. Sorry, I'm running out. Yeah, why am I not doing this? Sorry. Less than 2 capital T. So I obtained a piecewise solution for this region as well. Now I will erase some things. This one, for example, these red things, this red thing, and these. And then I will take with a lasso again. And I will slide it further like this to here. Okay. Now, of course, I have to erase this T because T is now here. This is T. And this T, as you see, is greater than 2T. So the region that I'm taking is T is greater than 2T, but less than 3T. Because if T is greater than 3 capital T, it means it's completely to the right-hand side and nothing overlaps. So within this range, what is the intersection that we are dealing with? The intersection that we are dealing with starts from here, this point, because to the left of it, h of t minus tau is 0, and it ends at capital T. So within this range, we have a shape, and that shape's area that we will evaluate corresponds to twice the area of this trapezoid. All right. Now let's find the area of that trapezoid. For that, we need to know some critical points. The first point is the top of this triangle, which is T, because its width is T, height is also T, that kind of a triangle. And this point here is T minus capital T. So what's the area of the trapezoid? Again, it's the difference between a larger triangle, and from that larger triangle, I will remove the area of this green triangle. Okay, that's the thing that I will do again. The larger triangle area is T square over 2, 1 over 2 T square. That's the area of the larger triangle. The green triangle, however, is minus 1 over 2 T minus capital T squared, like this. Yeah, the height. Oh yes, excuse me, you're right. Özkan Kaya tells me that the height of the larger triangle is 2 capital T. It's not T. Yes, you're right. It was the previous case, so I have to correct that one. Thanks. Yes, the height is 2 capital T, because the width of the triangle was already 2T. Look at what we have here. And the height, as you see here, is indeed the height of the triangle is 2 capital T. So thanks for that correction. Otherwise, I would be making a mistake. So this is not T square. The area is not T square. The area of the larger triangle is 2T squared with a 1 over 2, like this. So this is the area of the red portion. And then we have to multiply everything by 2 because, sorry, excuse me, because the x of tau value, level value was 2. So the area will be multiplied by 2. And what does this make? By the way, this is the last area that we are discovering. So 1 over 2's cancel, and we have 4 capital T squared minus T squared minus 2 capital T T plus capital T squared. Let's make this the subtraction, and it will give me 3 capital T squared plus 2 capital T T minus capital T squared. And when is it? It is when T is between 2 capital T and 3 capital T. So we just write it like that. What was that? It was 3 capital T squared plus 2 capital T T minus T squared for 2T, between 2T and 3T. So we need some further place. What happens if T goes beyond that 3T? Then it means this triangle completely falls out of the range. Let me just illustrate it very briefly by erasing these and putting into a I hope I will be able to grab this shape. And we just take it out of everything like this. And then clearly x of tau and this h of t minus tau, they don't overlap. Their multiplication is 0 everywhere. And when you integrate the 0 of that kind of an overlap, you get nothing. So we can say that it's also 0 for t greater than 3t. Maybe you can put equal anywhere, because in the boundaries of these piecewise equations, the equations will give you the same thing. For example, check out this one and this one at t is equal to capital T. Oh, sorry, at t is equal to 0. Excuse me. At t is equal to 0, t squared is also equal to 0. So it doesn't matter where you put this equality sign, here or maybe here. It doesn't matter. And now check this thing with the next equation and check what's the value for t is equal to capital T. When t is equal to capital T, this line will give you capital T squared, and this line will give you 2 capital T squared minus capital T squared, which is also capital T squared. So, you know, these equalities may exist anywhere, and it doesn't really matter which one you prefer, because they have exactly the same value. That exact same value is guaranteed because these signals of x of t and h of t are not impulsive. They don't have any infinite values or impulsive values. They have finite values. They may be discontinuous, it's okay, but they have finite values, and because of that, the convolution output will be a continuous shape. It doesn't have to be differential, but it will be continuous, certainly. And if you give me the result like this and put it in a box, and when I see it, I will give you 10 points. That's the convolution of these two shapes, of this shape and this shape. Okay, so this is how we do convolution in continuous time. You will be able to find continuous time convolution videos everywhere. If I can find them, I can share some of the links with you as well, because it just flips around one signal and slides over the other one to see what kind of an output it generates. This is not a very simple example. One of them is triangular, the other one is rectangular, and I'm also discovering the shape in terms of analytical expressions. I don't give it as only a graph. But for rectangular convolutions, usually people just give you some plots, and that will be easier than this example maybe. Next week, we may continue with some further continuous time convolution examples. They are critical. Yeah, so that's all I want to talk about for today. We have already this has been a long lecture actually, but this example itself is the continuous time convolution, which is necessary. And we cannot finish it before this many minutes, so you have to spend this time. So now, any questions regarding continuous time convolution? Usually students just like continuous time convolution more than discrete time convolution for some reason, I don't know. Maybe there are more questions from that, and while exercising, you will learn this better. You flip around one of them, slide over the other one, look at the multiplication, crop the boundaries, find the area of the multiplication, and see what the output will be. We will see a few more examples from here. All right, so if you don't have any further questions, I can stop at this point. It may be already a bit tiring. You may be tired. Or if you have questions, you can ask. You may collect your questions for the next week. An irrelevant question. Konuyla alakalı değil ama herhangi bir quiz planlıyor musunuz? You know, the idea of a quiz is that it is pop quiz. So we don't plan. We do or not. So if I say that I'm planning to do a quiz, then it wouldn't be a quiz. It would be a scheduled examination or something like that. Would you like to have some quizzes? He says, thank you. What do you mean, thank you? Thanks for the explanation, I guess. But, you know, it's been, I'm a bit lazy for this, because for a quiz, it must be a test. And what is good about doing a test for this kind of such an analytical course, right? Because if I give you a quiz, how many people are you right now? You are 68 people. You are not a lot, but normally you must be more crowded. Let's say that I did a quiz and 100 attendees just answered the question. It's a headache to make an assessment and evaluation of those for 100 students. So yeah, probably I won't do that. And it is bad for you. I'm not going to do that because I don't have an assistant to take care of your input. The assistants are very critical for evaluation purposes, for quizzes, not for the exams. The exams are the beauty of being evaluated by the professor, but the quizzes could be checked by the assistants. Unfortunately, I don't have any, so I can't do that. I cannot read so many quiz answers. It will take me hours to do that, which means you have to exercise on your own, unfortunately. And please, please, I'm begging you, literally, to exercise and solve questions. There are so many beautiful questions everywhere, and only by solving those questions you will be fit to perform well in the examination, the midterm, or the final. Okay. Otherwise, you may say that, I understood this problem, but of course, in the questions, the problems will be more complicated than this one. So exercising is important. Anyway, so I'm stopping the recording now. Hocam, tek arasından varsa daha geç olur herhalde, değil mi? Yes, the timing of the midterm, it must be somewhere between the first and the second midterm in regular terms. Right? It will be, of course, later than the first midterm date, but earlier than the second midterm date, somewhere in between. It must be given already. I just don't remember. Just continue exercising, and when the date comes, we will let you know, and you will be ready for that. Don't worry. Okay, now I'm stopping the recording.